Thermodynamics is a very broad topic. I am going to just address a few of the concepts in thermodynamics. So first, let us define some terms. When we talk about thermodynamic system, what we mean is that we're just isolating part of the universe that we're interested in studying. And then everything that's outside that system will be the surroundings. Now, there are different types of systems that we're going to be looking at. One of them is an isolated system where the system does not exchange any matter or any energy with its surroundings. A second type is a closed system, and in a closed system there is no exchange of matter with surroundings, but the system does exchange energy with the surroundings. Then an open system is open, as the name suggests, which means that the system exchanges both matter and energy with the surroundings. Now, we will have to look at the state of a system. So when we're talking about a state, we mean that we're looking at a set of properties of this particular system. There are various different kinds of properties that a system can have, like the pressure, volume, temperature, internal energy, entropy, density. So there will be a unique set of these properties that the system will have at a particular point. We will want to go between two states, so the system will develop from one state to another along a process. So the process is the path that the system takes between any of these two states. So we can say that at a particular state 1, the gas, if our system is a gas, has a certain pressure, volume, and temperature, and then following a process, the gas will have a different set of pressure, volume, and temperature. So there are two quantities that are functions of the process, and those quantities are work and heat. So in thermodynamics, we're interested in the three types of energy: internal energy, which is a property of the state, and the process, which are work and heat. So we normally talk about the change in internal energy, because when we look along a process, then from state 1 to state 2, energy changes. So we're going to talk about that change in internal energy, whereas work and heat will just be specific to the particular process. Now we have to define what a positive and what a negative work and heat are. So unlike in chemistry, in physics, work is positive when the system does work or it expands, and it is negative when the work is done on the system, so the system is compressed. In chemistry, work is defined in the exact opposite way, where work is positive when when work is done on the system, but in physics, work is positive when the system does work. Heat is positive when the system gains heat, and it is negative when the system loses heat, which is the same as in chemistry. There are 4 special types of processes, and those processes are isobaric, isochoric, isothermal, and adiabatic. We will talk about these different processes more in depth in a different lecture. There are 3 laws of thermodynamics, and I wrote here a +1 because actually there is a very, very basic law, and that is now called the Zeroth Law of Thermodynamics. And that Zeroth Law says that if a system A is in thermal equilibrium with a system C, and a system B is in thermal equilibrium with a system C, then systems A and B are also in thermal equilibrium. So what this really means is that if temperature of system A is equal to temperature of system C, temperature of system B is equal to temperature of system C, it is pretty self-explanatory that temperature of A is the same as temperature of B. So that's why we call it the Zeroth Law of Thermodynamics. The first law of thermodynamics says that for a closed system, the change in internal energy is equal to the heat gained by the system minus the work done by the system. Now, I prefer writing my first law like this, where I have the heat is the change in internal energy plus the work, so that I don't have to worry about the minus sign. Does it go in front of the Q or does it go in front of the W? This way, Q is change in internal energy plus work. The second law of thermodynamics has two different ways of looking at it. One of them says that heat flows from a system with high temperature to a system with low temperature. So we know that that's the case. If we want the system to go from low temperature to high temperature, we actually have to do work on the system to make that happen. But spontaneously, heat will always flow from a system with high temperature to a system with low temperature. The other way of looking at it is that energy in a system will spontaneously disperse, or the change in entropy is greater than or equal to 0. So there is a greater than or equal to here. In an irreversible process, and most processes in our universe are irreversible, the change in entropy is going to be greater than 0. So we'll say that the system goes to a higher disorder. For reversible processes, we have the equality, so the change in internal energy, the change in entropy is equal to 0 for a reversible process. But again, most of the processes in the universe, if not all, are irreversible. We can just assume that from one state to a very close, minute state, higher than that, different than that, the process is reversible. So we pretend that the processes that we are going to be working with are all reversible. And then the third law of thermodynamics says that absolute zero is unattainable. So that means that 0 Kelvin is a temperature that we can't cool things to. So if the universe were at 0 Kelvin, then everything would stop, nothing would move, everything would be dead. So absolute zero is unattainable.